we'll get started, right. So, the goal today is to modify the programs that we already have, all right, to visualize the aspects of the waveguides that we have just analytically solved, right. You need to know how to modify the program in order to see the effect of the waveguide, etc. Right. And in specific, since we are dealing with 2-dimension space, all right, in the case of simulations, we'll take a look at the parallel plate waveguide case, right. For the rectangular waveguide, you may need to write some 3-dimensional Maxwell equation code that will have Ex, Ey, Ez, Hx, Hy, Hz, and you will have solution in all the 3D space and 1D time. Then you have to take a slice and solve. It's too hectic, right. So, in this case what we are doing is we are reducing the problem from 3 dimensions to 2 dimensions. First of all, parallel plate waveguide, you can just draw it as one conductor on the top, one conductor in the bottom, filled with some material inside. So, it can be represented in the cross sectional form. So, what we are doing is, instead of looking at the cross section, we are looking at the longitudinal side, right. We are going to launch from one side and we are going to observe what is going to happen, right. For this, we had already written a code for perpendicular polarization, all right. So, I am going to open that code and I am going to start making modifications to plug in the waveguide, right. Okay. All right. Okay. So, I am going to keep most of the things consistent here, all right, the same way what we had it before. I think towards the end we had plugged in another material, all right, on the right side. So, we had talked about dielectric interface using this code for perpendicular polarization. What I am doing is I am just getting rid of that particular interface, right. Do you have computer? Think maybe. And you have this code already with you? All right. Okay, I am going to the region in the code. So, I am having perpendicular polarization code that we recently wrote. So, you can open it if you have it, right. So, I am just getting rid of this interface because I do not want this dielectric interface. I just want a region of vacuum with 2 plates present inside of it, and then I am going to run some experiments on it to corroborate whatever analytically we saw, right, that is all. So, I am getting rid of this. I also do not need a plot of permittivity. So, I will get rid of this and I will save it as a new file. Okay. Inside we had written the vector update for Hx, Hz, Ey, all right. And the first step that I will do is make sure that my program first runs and then I will start making modifications. I have removed a couple of lines, I will just make sure that my program runs and then I will start making some modifications to it. So, I will reduce the amount of time to say 100 time steps just to check what is happening. Okay. Seems to be running. All right, a few things that I will do very quickly is I want to make sure that my axis is not changing with respect to the colors, because it is very wild if your color bar is going to be changing from minus something to plus something for every time step. So, I want to fix that bit to between -1 and +1 so that I can make proper inferences, right. So, in the image.sc command I am just adding a limit of -1 to +1 for the color bar. That is the first thing that I did, right. Now, I can start manipulating this code. Okay. So, now we have a code for perpendicular polarization and I want to create a parallel plate waveguide, all right, and then start experimenting with the code, right. So, how do I define a parallel plate waveguide? I know that I need to have 2 conductors, right. The way I tell to the code that I have 2 conductors is by making the electric field 0 at specific places. So, I look at the components that I am having in this particular simulation. I am having Hx, Hz, Ey. Okay. So, what I could do is I could just take Ey, make it 0 at the places where I want to define the conductor. Okay. So, what I am doing here is I go inside the for loop. Okay. I am just going to say that maybe just before the source, right. Right. Maybe even after the source, does not matter, oops, right, does not matter. So, just around this place. So, to be consistent, what I will do is I will just do it after I define the source, right. So, I am just going to take some region which let us say that I am having 100 by 100 space, right, 100 points in one dimension, 100 points in another dimension. This all right. So, what I will do is I will create something around the middle. So, I will just do maybe 45, right, comma colon is equal to 0. So, at x position 45, at all points in y, I have made the electric field manually equal to 0, which means that according to the code I have placed a conductor in this line, all right. Now, I want to place another line, all right. So, I will place it symmetrically on the other side, right. So, I will just make it 55 comma colon and I will make that equal to 0. Okay. So, I have x dimension of 100, y dimension of 100, the middle point will be at 50. So, what I have taken is I have taken a line above 5 grid points above, 5 grid points below, and I have placed some 2 lines where the electric field has been forced to 0. Now, the definition of parallel plate waveguide is done, all right. Let us run the code and then start making modifications to it, and then slowly we will start seeing what is going to happen, right. Okay. So, I have something previously when I did not have this code. So, I will just comment this out, right, and run the same code again. I notice that in both the cases definitely the field patterns are different. So, those 2 lines are having some effect, all right. One of the cases here where the lines are commented, I noticed that I had a point source on the left side and it is clearly diverging and producing some circular wave fronts, all right. Whereas, in the case when I had the 2 conductors, I do not have this diverging thing happening, all right. I see that something is traveling from left to right. So, that gives me hope. Now, I will start looking at what else is going on, right. Okay. So, also one of the things that I notice is that it's giving plots for every instant of time. So, I am just going to make it easier for me. So, I am just going to say that if n, let us say that if modulo n2 what I have done is n is the time loop that we are considering, n is equal to 1 to time total. If n is divisible by 2, I am making a plot. That means for every 2 time steps I will get 1 plot. That way at least I can have a faster execution of this code, right. So, I will just run it once again to verify, right. So, now I see that there are jumps, all right, it is going from 40 to 42 to, right. Later on, depending upon the need, I may change this to lesser number of plots or not, right. Another thing that I am noticing here is that I am having a square region, all right. When we are talking about waveguides and we are talking about parallel plate, I think it has to be clear that one side is longer than the other side, then we know which side it is traveling, all right. So, I think I will just make that adjustment also. So, I will just make my Z dim to be say maybe 2 times or 3 times longer, right. And I will also increase the amount of time to 400, right. Okay, now I will maximize this, it is much better. Okay, I am having a source on the left hand side and then I am having 2 plates, right. Okay, clearly I am noticing something odd happening over here. That is, I am having a source and as it travels through the waveguide, I am noticing that there is an attenuation of some kind, alright. So, first it has to give me a clue that maybe there exists a cutoff frequency, alright, for this waveguide, and maybe we are close to that cutoff frequency, maybe we are just above the cutoff frequency, or maybe we are very closely approaching the cutoff frequency, right. So, let us see if by manipulating the frequency of my source, I am able to get a much better well defined propagation, right. So, that is the first thing that we will do. So, what I will do is I will go ahead and in the source definition, I would have used a sinusoid, right. So, I am having sin n by 4, right. So, this is telling you with respect to the amount of time. So, in order to increase the frequency, what I can do is I can make it sin n by 2, okay, and I am going to run this program again. Seems like that fixed it, right. So, now we have to verify whether we are right or not. So, we want to go well below the cutoff, alright. I have not calculated any cutoff frequency here, I am just going to determine it by doing these experiments, alright. Okay. So, it has travelled and I do not see any exponential decay or anything happening over here. So, it is clearly guided wave travelling between 2 plates and it is going from one side to the other side. And I would like to verify if this is truly an issue of the frequency. So, what I am going to do is I am going to do the exact opposite. I had sin n divided by 4, made it sin n by 2, I will make it sin n by 10 to just see what happens, alright. Go to the exact opposite direction and see what happens. Alright. So, it is clear that we are not able to launch electromagnetic fields into it, alright. So, first of all, the way to visualize cutoff frequency should be clear. Even if you are not aware of the formula, alright, it should be possible for you to take the code, just sweep the frequencies of the source and try to get a decent estimate of what your cutoff is going to be, right. Now, I will stop this, then I will go to my theoretical study that we had. If I go back to the notes, I would like to see the formula for the cutoff frequency for the parallel plate waveguide. So, I have f cutoff is m v1 divided by 2d, alright. Now, in this particular case, I have changed the operating frequency to go higher than say f cutoff, etc. But in the program, nowhere I have mentioned what mode I want to excite m, I have not given anything, alright, and the d is kind of fixed in the way we have written. So, d is the separation between the 2 plates. So, in one case, one plate is at 45th coordinate and the other one is at 55th coordinate. So, you can say that the d in this case is 10 spatial steps, alright, 10 spatial steps, that is good enough. V1 again we do not know, it has calculated from whatever epsilon, mu and the parameters that we have given. So, we do not care, but now I want to make some sense out of this, right. What I what I understand from this particular expression here is that the cutoff frequency inversely is proportional to the separation, right, which means that if I did increase the separation between the 2 plates, alright, frequencies which were not passed before should start passing. Okay. So, your cutoff frequency has to reduce. For example, in our case sin n by 2 was passing, n by 4 was decaying, n by 10 was almost not able to pass. Now, what happens if I say increase the width or the separation between the two plates, right. So, I am going to go ahead and go to the region, I am just going to make it 30 and 70, all right. So, the center line is 50th space coordinate. Now, I am making my waveguide 30 units on the top, 30 units at the bottom. So, I mean no 20 units on the top, 20 units in the bottom. So, it has become 40 space units separation between the two. Now, I want to keep the frequency same at n by 10. Previously, it was not passing. I want to see whether it passes now and whether it has an effect on the cutoff frequency, right. Let us go ahead and do it. Right. Now, immediately I notice that I may have to make a modification because the source is defined at a single point, but the waveguide width is large. So, the energy is spreading through the area of this waveguide and the intensity of the spots is becoming lesser. This gives us the illusion that maybe something is happening, but what we will do is we will increase the intensity at the point source and then we will start to look at it again, right. So, in order to increase the intensity, all you need to do is multiply this with some constant. So, I can just put 3 times etc., right. So, I will just run this again and then I will try to see what happens. Okay, seems like I am able to launch, all right. So, if I change the separation between the two waveguides, all right, clearly the cutoff frequency reduced, all right, but I have still not said which M I am willing to excite in this waveguide, all right. I am not giving any parameters, I have put a source. It appears that for this configuration a particular pattern of electric field is being created, all right. Now, in this case there are a lot of things happening, let us look at them one by one. First of all, you have a configuration of the waveguide and the source is placed as a point perfectly in the middle of the waveguide, all right. Now, let us look at that a little bit more carefully, right. Where is the source? Okay. So, I have x source minus 1 to x source plus 1 and all that. So, there were 3 points which were emitting. So, what I am going to do is I am going to fix it to something that I am already aware of. So, this was between 49 and 51, right. So, I am going to move this, I know that the center of the waveguide is at 50. So, I am going to move this to 60. Okay. Let me just tell you this again. So, 30 to 70 is the extents of the waveguide, 50 is the center of the waveguide. Previously this point was at 50, now I have moved it to 60, which means that now it became asymmetric, all right, with respect to the waveguide, all right. So, it is slightly going towards one direction more than the other, all right. And in order to keep my analysis simple, I will also try to increase the frequency to say an hour 6. I can notice that the pattern that it produces is very different than the pattern it was producing when the source was placed right at the center, all right. Once again, we will do this for a slightly different configuration. I will reduce the waveguide width a little bit because this is overly exaggerated. So, I will just make it a little bit shorter, right, so that I can get my point across. Right. Oops, I am having it right at the. Okay, now I notice something weird has happened. Previously, when I had the plates to be wider, when I kept a source largely asymmetric, I started to notice different pattern, alright. Now, I made the plates go a little closer to each other and I kept the source reasonably asymmetric, I would say, but still I noticed that the pattern is similar, right. This should tell us something about the way we are making a choice of M in the case of these waveguides, alright. It is telling that first of all, when the spacing between the waveguides was very large, okay, and your source is of some frequency, maybe the number of modes that can be supported by the waveguide is higher, okay. And if the number of modes supported by the waveguide is higher and if your operating frequency is above the cutoff for more than one mode, then you may be able to excite more than one mode, alright. That is why you are getting some very different patterns when you move the source from top to bottom of the waveguide, make it asymmetric, etc. But if your plates are going to be closer to each other, the number of modes that you can excite for a given operating frequency is lesser, maybe it is just one in this case, right. So, it really does not matter. In order to validate this theory, what we will do is we will make the waveguide even narrower and make the source highly asymmetric, that is it is almost touching one of the conductors, right. So, what I will do is I will make it 45 to 55 and I am going to put the source at 54th point, right. So, now the source is really not at the center, it is close to one of the plates that you are using. So, it is highly asymmetric excitation, right. Okay, now I have run into another problem that can be fixed. I overlooked that problem. The frequency, alright, because I have changed the width, alright, the operating frequency also has to change. Maybe clever thing to do is sin n by 2 and then redo this again, right. Alright, now I get some propagation. But now there is an issue. Sin n by 2 means that you reduce the frequency, right, you increase the frequency, you increase the frequency, but if you increase the frequency of operation, right, you made some adjustments to the width of the waveguide, that was valid for the frequency you were using before. Now again, for this operating frequency, for this separation, how many modes are separated has to be recalculated, alright. In this case, I can clearly notice that there are multiple patterns which are emanating, alright. Either it is like this or it is something like this, alright. Means that this particular waveguide for this particular frequency is still a multi-mode waveguide, alright. So, at this frequency it is still multi-mode, alright. Yeah, but in the it will be like that, there will be some beating between them. Yeah, but there is no direct way to predict at which spatial location, at which instant of time you will have which field pattern, that is all. They are just, it is just beating. You are having more than one mode, they are beating with each other at different instants. So, now you saw that towards the end it was single mode, if you run it for more time, that pattern will change, right. So, that is why it is easier for us to operate a waveguide under single mode condition, so that you do not have this confusion as to what kind of pattern will be present at what instant of time in what space, all right. So, I think the best way is to increase the decrease the frequency a little bit of operation, right, and see what happens, right. Okay. Now, it is still a highly asymmetric excitation, right, but I have changed the frequency of operation by keeping the waveguide dimensions fixed, all right. What I am noticing here is that I am seeing only one kind of pattern emanating between, right. So, it tells that in practice, all right, in practice, if you want to excite multiple modes, all right, you could do that with a point source that is placed in different locations between this waveguide. So, maybe if you placed it exactly symmetric, maybe you will get some kind of a pattern, but if you moved it towards one plate or the other plate, you may excite the other modes, right. So, we always have this question, what does this multiple modes mean and how do I excite these modes? Usually a point source gives out light in all the directions, all right. So, you could use a point source to excite all the modes, but if you want to exaggerate the presence of these modes, then you can move them in the cross section of the waveguide, all right, that will give you an exaggeration. But a truly single mode waveguide, no matter where you excite it, right, will eventually form a single mode pattern only, all right. And in this case, it is just by adjusting the frequency I was able to get this pattern, right. The other thing that we can start looking into is, right, make it extremely big, go back to it 30 to 70, have a source that is not a point source. So far we have been dealing with the point source, all right. Also it is worth to notice that suppose you do not have control over your configuration like a point source. For example, if you say that your waveguide separation is 1 centimeter, your source needs to be, say for example, a millimeter or lesser in size, so that you could consider it as a point source in practice. Suppose you do not have something like that, you have something which produces a collimated electromagnetic wave as the source, then that may have some beam width, right. Let us say that we are going to now see the properties of the width of the source on the waveguide. Let us take a very wide waveguide and let us say that from 30 to 70, okay, the entire width of the waveguide, you are having a source, that is you are having what is known as a line source instead of a point source. And we already know from our previous runs that in a line source you will start getting plane wave fronts, right, and then let us see what the waveguide does to it, right. Seems to be okay, seems to be launching like a single mode pattern. Hard to say because in between some interference patterns are definitely occurring, all right. So, it is hard to say, but seems like it is easier to control this, all right. The other thing that we can do is make it a little bit smaller, all right. I am just making it a little bit smaller, maybe 40 to 60. again hard to say what is going on. It seems like there is propagation, but there is some strange interference patterns which are coming into the picture. I think we will have to reduce it further, and let us say that it goes from 40 to 60. So, this will become 45 to 55. Okay, now it is possible to say that maybe this waveguide is supporting multiple modes, and I can see that in some regions it is forming 2 spots, some regions it is forming 1 spot, etc. Right. So, clearly the electric field distribution across the cross section is different in different places, right, and there is some periodicity happening, right. So, size of your source could also determine how many modes you are exciting probably, right. So, in practice, in order to avoid all these complications, people try to use a source that is as wide as your waveguide, okay, and also try to make sure that at the frequency of operation, whichever frequency you are choosing, at that frequency the waveguide supports only say one mode, alright, and the fundamental mode is what you want to operate with most of the cases, unless there is some explicit need to excite the higher order mode. There may be specific application where they want to have different mode patterns or different field patterns. Unless there is some requirement like that, this is how people would do it, right. So, now this part is now very clear, alright. Now, we will just make a couple more things, right. I had a waveguide going from left to right, okay. Now, what I am going to do is I am going to introduce a 90-degree bend, okay, but I am going to make this an abrupt 90-degree bend. So, I am going to launch it from one side, right, and I am going to abruptly try to see what would happen if I kept a perfect conductor 90 degrees, alright. So, that I would really know whether it is doing some waveguiding or not. In fact, the essence of waveguiding is I should be able to take it from one region, guide it to some other region which is not exactly in the line of sight, right. So, now we will go ahead and do that, but we will also remove some of the unnecessary parts. I will make the waveguide narrow again, alright. So, it is easy for me, right. So, I will make it between 45 is what we saw and 55, alright, and let the source be as wide as the waveguide, and I will also choose a safe frequency to operate, okay. Now, I want to insert 2 plates. So, originally I had EY at location 45 for all positions in the other axis to be equal to 0, right. Now, I want it to go only till the middle, let us say, right. So, I will just say that so 45 is at the bottom. So, one of the plates has to become a little longer than the other plate, because I am having parallel plates, I want to have parallel plates here also. So, one of these plates has to become longer, alright. So, I just do not remember how we were, how the axis was. I will just run this and just note down. So, 45 is here, okay. So, the 45 plate could be longer, right. So, this goes from 1 to middle point of this was 150. So, 155. Okay. Now, I have just made 2 plates, one plate 10 units longer than the other, which is the width of the waveguide that I have chosen over here, right. So, I will just run to make sure that I am getting something on the other side. I have not inserted the second pair of plates over here. So, about the center is where we should see that something happens. It should start exiting the waveguide. Okay, because one plate is longer than the other, it's actually directing a lot of the energy to the bottom side. Now I want to keep a second pair of plates going from the middle to the bottom, and I want to see what's going to happen. That's all. Right? So I'll keep the plates once again. I think it's easier for me if I note down the coordinates. Let me just run this briefly, just note down the coordinates where I want 55, 145. Okay. So I'm having 55 to 100. Right? I have another plate. Okay. If they are wrong, I'll correct it as we go. I think it's correct. 55 colon 100 comma 145, 45 colon 100 seems fine to me. Okay. So now I'm going to run this again. Okay, now I noticed something that we have not seen or studied about before. All right. We have talked about positioning of the source to create different modes. We have also talked about the width of the waveguide that can support different modes. And in this particular case, I had used a line source to excite this parallel plate waveguide. I assumed it to be single mode, but when I inserted a 90-degree bend, I noticed that the pattern that's coming in this 90-degree bend is very different from the pattern I was getting in the horizontal section. And this reminds me of something very clear. All right, it shows here that if I go from one side to the other side on this waveguide, I am having electric field 2 spots. All right, I am having 2 spots, 2 half cycles I am having. So this corresponds to m equal to 2. All right, and on top of that, in order to validate this, I also remember that electric field in one spot is 180 degrees out of shift with respect to the electric field in the other spot. So clearly one is red and the other one is blue, corresponding to +1 and -1, and this clearly tells me that yes, I am looking at m equal to 2 spot. Okay. So this means that when you take a waveguide and when you make a bend on it, all right, you will start seeing the modes that are present. The second thing that you are noticing is that what's more interesting is that we launched and the pattern appeared to be predominantly fundamental mode. Fundamental mode had one spot. The fundamental mode did not pass through this abrupt 90-degree bend, all right, which means that it may have hit this wall and it is getting reflected back in the horizontal section and it is creating an interference pattern, all right. Whereas the higher order mode, all right, is actually doing something different than the fundamental mode. Maybe it's doing multiple bounces and the way it is traveling is very different from the fundamental mode, all right. And it's also clear that when you had an abrupt bend, the higher order mode passed, the fundamental mode did not pass over here, right. So, these are all some things that we have not studied analytically, but this program now gives you, some starting point to make experiments with structures and try to see what all things can happen. So, it means that in order for me to do a real experiment, okay, I need to have a source. The source could generate, the source should be of the size of the waveguide, all right, in order to excite some clean waves inside of the waveguide. And in order for me to detect that I am having waveguiding action, I could keep a detector on the other side. But normally, if you keep a source and a detector on the same side, I mean in line of sight, it is hard to believe that you are getting the light directly from the source or you are getting it through the waveguide. You will have trouble believing it, all right. So, a better idea would be to bend the waveguide in some way, all right, so that your source and the receiver are not in line of sight, and then actually prove that you are really having waveguiding action, all right. And one of the simpler things one could do is make a 90-degree bend, but it seems that if you make a 90-degree bend, all right, you are going to be able to measure the intensity, but the mode pattern is dependent upon the size of the waveguide, again number of mode it supports, the frequency of operation, etc., right. In order to do this once more, what we will do is, instead of n by 2, we will just see if we can do n by 3, all right, and just see what happens. Clearly, this waveguide is single mode, right. So, what happened is, it went, a portion of it started going through the 90-degree bend, and it did not change the mode configuration. But normally one would say that, look, it is not a very conclusive thing. Only thing you can say is, you are getting light from this side and it forms a specific mode pattern, and the light is coming from the other side, it is forming a specific mode pattern. You cannot conclude that it is a single mode, multi-mode and all that, because maybe multiple modes are there and you did not excite it, or the configuration is such that single mode was dominant and then it did not get converted due to several other reasons. But it is clear that, the operating frequency, the size of the waveguides, the bend that you have, the size of the source, all of these are ways for us to excite and, probably propagate different kinds of modes in your parallel plate waveguide. Okay. So, I think with this 90-degree thing, it should be clear that indeed you are seeing some waveguiding action. So, many people make modifications of this. You may also choose, for example, instead of having a structure like this, you may choose to put a metal on the right edge of the waveguide. So, it is a very different case where you have a source, you have a waveguide, and then you have a metal plate at the edge. Okay. So, you will be having waveguiding action, and then at the edge you are having some complete reflection back. You can push this to one more extreme and say that you put the source right in the middle of a metallic box. Okay. It is covered with plate on all 4 sides in the cross section, 2 sides in this way. In those cases, the energy will not be able to leave the box. It will keep on bouncing back and forth, back and forth, back and forth, and it will keep on being present inside the box. So, you can use the analysis that we had, and in several books there are some treatment about cavities, resonators, etc. These are all extensions of the same concept. So, you start with single interface, now we had 2 interfaces and all that, right. Now, you can go ahead and use the same approach to put metals at different places and build what is known as cavity, resonators, etc. You could also study about what is a resonant cavity, what is a non-resonant cavity, all these things. So, we have the framework. Unfortunately, we will not have the time to study each and every component, this RF and photonics, but I think that now you should be able to understand that you have the starting point and you can use your imagination to navigate a little bit further. And another advantage is you have a program, right? You can do any arbitrary non-physical thing also in a program. You may be able to easily put a source in the middle, cover it with a box and see what happens. It may be tougher to do that in an experiment actually, right? So you have the foundation. I hope that you will make use of it and see what all you can do with it, right? So we'll stop here. The next class will continue.